using it. More people in communication, they always like to use Mac.
We've discovered more about the world than any other civilization before us. But we have been stuck on this one problem. How do proteins fold up? How do proteins go from a string of amino acids to a compact shape that acts as a machine and drives life?
When you find out about proteins, it is very exciting.
You could think of them as little biological nanomachines.
They are essentially the fundamental building blocks that power everything living on this planet.
If we can reliably predict protein structures using AI, that could change the way we understand the natural world.
Protein folding is one of these holy grail type problems in biology. We've always hypothesized that AI should be helpful to make these kinds of big scientific breakthroughs more quickly.
And then I'll probably be looking at little tunings that might make a difference.
You should be creating a histogram one and a background histogram.
We've been working on our system AlphaFold really hard now for over 2 years. Rather than having to do painstaking experiments, in the future biologists might be able to instead rely on AI methods to directly predict structures quickly and efficiently.
Generally speaking, biologists tend to be quite skeptical of computational work, and I think that skepticism is healthy and I respect it, but I feel very excited about what AlphaFold can achieve.
I'm going to read an email. I got this from John Malt. I'll just read it. It says, John, as I expect you know, your group has performed amazingly well in CASP 14, both relative to other groups and in absolute model accuracy. Congratulations on this work. It is really outstanding.
AlphaFold represents a huge leap forward that I hope will really accelerate drug discovery and help us to better understand disease. It's pretty mind-blowing.
You know, these results were, for me, having worked on this problem so long, after many, many stops and starts, and will this ever get there? Suddenly, this is a solution. We'd solved the problem.
In 2020, DeepMind's AlphaFold 2 solved a 50-year-old biology challenge. This is one of the biggest advancements in AI and structural biology in decades. The first thing to understand is that there are amino acids, which are the basic building blocks of life. Think of them like Lego blocks. With those Lego blocks, we can build proteins. So amino acids and proteins are both the building blocks of life, but they are also the machines that make life work. That's what allows us to see light, to move, to breathe, and to metabolize the things we eat. Each protein has an intricate shape that defines what it does and how it works. We know of over 200 million of proteins, and that number is going up as we discover more and more. But humans have been pretty bad at understanding the exact 3D shapes of all of these. So if we're looking at a Lego castle, we know which Lego pieces are used to build it, and we kind of know what the castle looks like. We just can't build an exact replica of it.
Unravel a protein, and you'll see it's like a string of beads made up of 20 different types of amino acids. Interactions between these amino acids make the protein fold, as it finds its shape out of almost limitless possibilities. For decades, a community of scientists have been working on a way to figure out a protein shape just from its string of amino acids. This is a major challenge in our understanding of biology.
Our ability to understand protein folding would allow us to understand the actual machinery that makes life function. The sequence of amino acids is folded into a unique and specific 3D structure, which determines the protein's function. It's important to understand that a string of amino acids can fold in many different ways. In fact, that's an understatement. To give you an idea, the number of atoms in the universe is 10 to the 82nd power. Yet the number of unique ways a protein can fold is 10 to the 143rd power. These are unimaginably large numbers. So basically, it would take an enormously long time to go through all the possible configurations. Yet proteins can fold in seconds or less. This, by the way, is called the Levinthal's paradox. So out of the 200 plus million of proteins that we are aware of, we were able to determine the exact 3D structure of about 170,000 of them. AlphaFold is able to take our existing data set of proteins whose structure we know, and then predict the 3D structure of other proteins that we do not know. This is an important thing to understand. Without AI, it takes us hundreds of thousands of dollars and years to map out these 3D structures. It's slow, it's expensive, and it's very limited. But with AI, we are able to have it predict new protein structures with ever-increasing accuracy. Why is this important? How will we use this newfound understanding in the real world? Well, the ability to understand protein function would allow us to know the unknown functions of proteins in our DNA, as well as quickly design new proteins that alter the functions of other proteins. This would be massive for pharmaceutical development, for our ability to understand and to change the genome. This would allow us to treat many diseases, create biomaterials that we can use in building as well as agriculture. Tissue and organ regeneration might be possible, as well as supplements for health and anti-aging, as well as many, many more things that we probably can't even think of right now.
AlphaFold's predictions could enable progress in all sorts of areas. Imagine a future where we can understand diseases more quickly and develop drugs to fight them, or one where we could use enzymes to break down plastic waste, or even to capture carbon from the atmosphere, all with the help of proteins. There's a lot more work to be done, but unlocking the shapes of these building blocks could help scientists better understand the natural world, and perhaps expand our knowledge of life itself.
This gives you such excitement about the way science works, about how you can never see exactly or even approximately what's going to happen next. There are always these surprises, and that really, as a scientist, is what keeps you going. What's going to be the next surprise?
When current medical science has run out of options and doctors don't know where to turn, artificial intelligence might be able to help, particularly when it comes to extreme cases.
It gives me hope.
Medics are getting more and more assistance from computer technology these days. We're not talking about any kind of superpowers, but valuable tools.
We don't want to get rid of specialist eye doctors. We want to empower them. We want to give them better equipment and make them better ophthalmologists who can treat patients more effectively.
They see artificial intelligence as a big opportunity, one that can take medicine into completely new dimensions. But some fear AI.
I can completely understand that AI applications can make people wary.
So what does artificial intelligence mean for medicine? How can it help to improve people's lives? Cornelia Nitzer hasn't been living in this small apartment in northern Berlin for long. The 63-year-old had never imagined that she would move home again, until fate turned her family's life upside down. Her daughter Anna Nitzer suffered a stroke shortly after the birth of her second child. Since then, she's been unable to move or communicate. The name of her condition is locked-in syndrome. It has changed everything.
Here you can see how pretty my daughter is. She was pregnant there, you can tell.
Her daughter needs round-the-clock care. Her son-in-law and grandchildren are on their own. Cornelia Nitzer is trying to do what she can to support the young family. It's been 2 years now since that fateful day.
She suffered brain hemorrhaging and a stroke. Someone from the neighborhood said that they must have spent about half an hour resuscitating her in the ambulance.
Cornelia Nitzer is only left with memories. Her daughter, a psychology graduate, was a happy, fun-loving person. Now her family can only guess what she's feeling.
She can't talk. If she moves like this, you can tell something isn't right. But you are helpless. You can't do anything, really.
Several times a week, Cornelia Nitzer helps her son-in-law with the household and with the children. so they at least get a bit of normality.
The children are suffering because they are without a mother. The girl is growing up without a mom.
The couple had just built their own home when Anna had a stroke. Her husband, Nikolai Nikiforov, was suddenly left to deal with everything on his own.
Kolya? Everything's open. Hi there. I'm here now.
The 37-year-old IT specialist often works from home. After his wife's stroke, he tried to care for her at home, but it was too much for him and the children. Nowadays, Ananitsa lives in a care home. Her condition, and then the separation from her, has placed a great strain on them.
The first year was very difficult. In the meantime, we've come to terms with it to some extent. We've got a routine set now. We visit her once or twice a week together.
But in the care home too, communication remains the biggest problem.
I visited Anna on Wednesday. She was quiet at first, but then she started crying. I think she still has bursts of pain.
Her family and nursing care personnel can only guess how Ananitsa is feeling. Recognizing the needs of locked-in syndrome sufferers and looking after them 24/7 is a strenuous business.
I've tried to work out a code with her. That a slow blink stands for yes and 2 blinks for no. But you can't call that proper communication. My biggest wish would be that this were somehow possible again.
The family's hopes are resting on research being carried out at Berlin's Charité hospital. Nikolai Nikiforov contacted scientists there a few weeks ago.
I came across a video by the professor. I think it was a TEDx talk where he showed what progress was being made in the treatment of stroke patients. My biggest goal would be re-establishing some form of communication.
Making this dream come true is what Professor Zoyo Zirkadar hopes to achieve with his research. The neurotechnology specialist is working on solutions that could help patients like Ananitsa to communicate again, using artificial intelligence and the communication between brain and computer. To put it simply, the human thinks and the computer acts.
It's my goal to improve conditions so as many people as possible can benefit from this technology and see their quality of life improve. And I won't let the setbacks slow me down.
Neurotechnology, which connects our nervous system with computers, aims to help people like Ananitsa have a new life. At Berlin's Charité hospital, there have already been successful tests with patients who are partly paralysed. Guido Schulze used to work as a painter. 2 years ago, he was diagnosed with a brain tumour. During an operation, a blood vessel burst in his brain. Since then, he's been paralysed on his left side.
I can't actively open or close my hand. I also can't even do it in my thoughts. When we are healthy, we don't give it a second thought. We just make a movement. And now I really have to try to do something, and it's not easy.
Today, Guido Schulze is testing whether he might be able to use his hand better by using a so-called hand exoskeleton. The wearable technology is controlled by his thoughts.
We are doing this so we can reorganize the brain. And this reorganization should have a favorable effect on restoring function.
Reorganize. It sounds as if everything here is jumbled up and will have to be sorted again.
The idea is that uninjured parts of the brain will take over the functions of the affected areas. Together with the exoskeleton, Guido is given a cat that can read his electrical brain signals. When the patient thinks about moving his hand, the computer recognizes that impulse and saves it, comparing it with the signals that his brain emits when he's not actively thinking. The computer is only able to learn because of the information that was taught to it by human programmers. They have fed it with algorithms and commands that help it increasingly better understand when Guido Schulze wants to move his hand. Like right now, the program understands what to do.
The bottle is now firmly in my hand. As a healthy person, you can't imagine it. It's crazy. You want to close your hand and it just happens. A bit spooky. Like something from science fiction.
The prototype is still being tested. Machines that can read your thoughts. That sounds frightening and is the source of much public debate. Many people are critical of artificial intelligence.
In my opinion, this form of intelligence cannot be compared with human intelligence. We're talking about computers that have been programmed to follow certain rules. If we raise awareness about how these systems actually function, it will become clear to everyone that they are not intelligent at all. They don't possess intelligence in the way we humans do.
Professor Zurkadar would like his research to help people in extremely difficult situations, such as Anna Nitzer trapped in her own body, or Guido Schulze, who is paralysed on one side.
The exoskeleton has stimulated my hand. That gives me hope that it might improve. I can imagine that if you train it over a longer period of time, that it will return to life. That's what we hope for, right? That it will get back to normal.
Stoppsignal mit Augen.
Here on the outskirts of the Austrian capital is where Oskar Slamala lives with his wife Heidemarie. The retiree suffers from age-related macular degeneration, or AMD. It can lead to a severe loss of vision. Fluid is collecting in his eyes and is slowly destroying his eyesight.
The worst-case scenario doesn't bear thinking about. It would mean that I would have to fundamentally change my life.
Oskar Slamala has worn glasses since he was a child, but one day, all of a sudden, his vision started to deteriorate.
3 years ago, I really started to notice that my eyesight was failing.
He did an Amsler grid test.
This test involves taking a piece of paper with a grid and covering one eye at a time. You look at it and see whether all the lines are running parallel or whether they look wavy. If they are wavy, it's a clear sign that something is wrong. The problem is that if it isn't treated quickly, it can lead to a loss of vision, and that is awful.
What's awful about the disease is that many patients suffer an extreme loss of vision, even if they do get treatment. Oskar Slamala hopes to avoid that by going for regular checkups at Vienna General Hospital. And patients like Oskar Slamala regularly get a drug injected directly into their eyes. But it's unpleasant and doesn't work well for everyone.
That looks good. How many injections has the patient already had?
He's already had 12.
Using magnification, the doctor can get only a rough idea of any changes to the retina. But it's hard to tell how far the disease has progressed from these white areas, which makes treatment difficult, and it's hard to know what dosage would be required.
We want to carry out as many of these injections as necessary, but as few as possible. Each injection into the eye hurts and carries the risk of infection. The medication is also expensive. It contains small, specially produced quantities of antibodies, and patients get these injections for the rest of their life. It's important that we do that as economically as possible.
It often costs €1,000 per injection. That's why the doctors in Vienna want to take a closer look at Oskar Slamler's eyes. An imaging procedure is used to give a cross-section view of the eye and retina. It lets the doctors better assess the extent of the disease.
Wow. Can you see the wavy?
The retina is raised there. The retina is very sensitive. It consists purely of nerve cells, which should not be interfered with. In this case, fluid is gathering under the retina, which is lifting it up.
But the procedure doesn't reveal exactly how much fluid has gathered there. So Professor Schmidt-Erfurt decided to design a program that can do just that. It was fed with the data of many other patients with the same condition, and it can tell exactly how much fluid pools under the retina, in blue here. The program allows Oskar Slamler's treatment to be tailored.
Knowing how this treatment works has given me a whole different perspective on things. Personally, I feel much more reassured.
Please take a seat. Today we've measured 45 nanoliters. That's roughly what it was last time, so we won't have to treat you today.
Thanks for the information. It's good to know these possibilities are now available.
It's a big vision for the future. This eye exam only takes fractions of a second. It's not invasive, is reasonably priced, and can be performed anywhere and assessed with the help of artificial intelligence. And it can replace many other invasive procedures.
AI can potentially make diagnostic detective work easier, keep medical costs down, and, most importantly, reduce human suffering. In Berlin, Anna Nitzer has come to spend 2 hours at home with her family. Professor Socrates' team has come to try out a new communication system with them.
I think I've seen this movie. I think you did too.
Don't record.
Yeah, I like it. I recall this one.
Super! 2 starke Männer und eine starke Frau.
Since her stroke, Anna Nitzer has been suffering from locked-in syndrome. She can't move her body, but she is fully conscious and can hear everything, yet she cannot communicate.
Ja, genau. So ist es.
The doctor wants to change that with the help of AI.
What we would like to achieve is to create an interface which is based on bodily signals that are very easy to control.
The aim is that Anna Nitzer will be able to learn how to communicate using eye movements. But the young woman's condition is different day to day. Sometimes she's just not up to it.
Anna, are you in pain again? I don't know whether to touch her or not. Well, she's crying. Maybe she's in pain, but we don't really know.
It quickly becomes apparent that Anna Nitzer won't manage to take part in the test today. But the family too needs to learn the system, so that they will be able to work with Anna independently. It's the first step on a long journey.
What we are seeing now is the simplest form of test, with which we can try to restore communication in locked-in syndrome, with blinking or eye movements.
The principle is that the computer learns certain eye movements and carries out commands associated with them. For example, turning a light on or off.
Man kann sehen, ne?
Look,
Jetzt mal
it
aus.
turns off and then on.
Jetzt an. An.
But it's not as simple as it looks. To work it, you have to be able to move your eyes both vertically and horizontally. Anna Nitzer can only do that now and again, and it takes a lot of effort. But the system nevertheless offers the first glimmer of hope to the family.
I think we'll manage it. We'll continue practicing with it. But also we have to take into account that Anna's condition also varies widely. It depends on how much concentration she can muster.
Today, her concentration is at its limit.